Recall our goal. We'd like to be able to calculate the surface area of a surface of revolution, which is created by revolving a curve around some axis of rotation. So for example, I have this little curved segment here. If I rotate it around the x-axis, I create a surface of revolution that looks like this, and I'd like to be able to calculate that surface area. And like we've done many times before, we're starting with an approximation. Specifically, we've just finished figuring out how to find the surface area of a frustum of a cone. If you recall, a frustum of a cone is created by taking a line segment, such as this one, and revolving it around the axis. And it makes a surface that looks like this, the frustum of a cone. So if specifically we consider a line segment, f of x equals cx plus d, between the points a, f of a, and b, f of b, the frustum created by rotating that line segment around the x-axis has surface area given by the following formula. The surface area equals pi times a quantity f of b plus f of a times a quantity b minus a times the square root of c squared plus 1, and here c refers to the slope of this line. And you just saw, hopefully, in the previous video how this was derived. Now, another way you may see this expression written is by taking this quantity here, b minus a, times the square root of c squared plus 1, and renaming it L, where L is just the length of the line segment. Okay, so you may see then S equals pi times f of b plus f of a times L. So what we're going to do next is we're going to see if we can generalize this to derive a formula for the surface area of a curve revolved around an axis. And a lot of what I'm going to do next is going to be very, very similar to the derivation of the arc length formula. So I'm going to assume that you've watched and hopefully understood that proof. So to start, I'm going to consider some curve f of x between x equals a and x equals b. And like I did when deriving the arc length formula, I'm going to divide this interval up into even subintervals, like so. And each subinterval will have width delta x equals b minus a over n. And then further, for each subinterval, I'm going to approximate the curved segment by a straight line segment. So if you look closely at my picture, you can see that I've done that, right? I had this curve in green, but then on each subinterval, I've approximated the curved segment by a little line segment. So let's zoom in on one of those line segments. Okay, so here I am, zoomed in on this line segment here, and that line segment that I'm zoomed in on is now the hypotenuse of this triangle you see here. And we've seen this before, right, in the arc length video. So when this line segment, the hypotenuse of my triangle here, is revolved around the x-axis, it's going to create the frustum of a cone, right? We just talked about how when you revolve a line segment around the x-axis, it creates the frustum of a cone. And so that frustum's surface area is given by the formula pi, in general, f of b plus f of a times L. But we can be a little more specific, right? B and A are the endpoints of my line segment, which here are xk minus 1 and xk. So if I fill that in, I'm going to have pi times f of xk plus f of xk minus 1. And then what about an expression for L? Well, L is the length of the line segment, or the length of the hypotenuse of this triangle. And we've figured out that expression before, and to do that we just use Pythagorean theorem. And if you recall, the length of this hypotenuse is the square root of delta x squared plus delta y sub k squared. Okay, so now I have an expression that gives the surface area of the frustum of the cone created by revolving this small line segment around the x-axis. Now, to approximate the area of the entire surface, that is, the surface created by taking this entire curve here, approximated by all these little line segments, and revolving that whole thing around the x-axis. Okay, so that entire surface. To get that area, we're going to add up all the little frustums, and that's going to give us the following expression. So what I've done here is I've just summed over all my subintervals from k equals 1 to n, and inside the summation here, I just have the expression which gives me the surface area of a single frustum for one subinterval. So now we want to recall the work we did in the arc length proof of rewriting this square root expression to get rid of the delta y sub k. I'm going to use the exact same steps here. So for an explanation, you should re-watch that previous video. So to quickly summarize those steps, I rearrange inside this square root in a way that allows me to pull out a delta x. And so I'm left with 1 plus the quantity delta y sub k over delta x squared under the root. And then I use the mean value theorem to rewrite delta y sub k over delta x as f prime of x k star squared. And now I'm going to do a new little trick. Notice my x sub k and my x sub k minus 1 here. So if delta x is really small, that is, my subintervals are really, really small, these x values, x sub k and x sub k minus 1, are going to be really, really close to each other. So I could say then that x sub k is approximately equal to x sub k minus 1. And I'm going to go one step further and say that they're both really close to a special point x sub k star that's in that same subinterval. Now, because f of x is a friendly continuous function, I can also say then that f of xk is approximately equal to f of x sub k minus 1, and that that's approximately equal to f of xk star. So now then I'm going to rewrite my summation using this little piece of information. So inside my sum then I'm going to have pi times f of xk star plus f of xk star, that quantity times the square root of 1 plus f prime of xk star squared times delta x. And then from there, I can write this as the sum from k equals 1 to n. I have 2 f of xk stars here. So I'm going to write this as 2 pi f of xk star, and then we'll keep the rest of this. Now, to make this approximation exact, I'm going to take the limit as n goes to infinity. That is the limit as the number of subintervals goes to infinity, which makes each subinterval smaller and smaller. And just like I've done in the past, I can write this, now this expression, this limit of this sum, as a definite integral. and that's going to be the definite integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. And this gives us a formula that will allow us to find surface area for any f of x with a continuous first derivative when that curve is revolved around the x-axis.